Yes. Okay. Okay. Um, the topic I have on the schedule for today, and also the one for next time, is actually something that was covered last semester in 460. But I put it on the schedule anyway because there are at least some people in the class who did not take 460 with me last semester. It would have taken it a prior time, and therefore, and the topics they're supposed to be consistent from year to year, but it hasn't really worked out that way for various reasons. So, and I figured review is a good thing anyway. And one semester is plenty of time to forget. So, but at the same time, I put it on schedule also because there are certain ideas from there that I need for new topics that will be coming up pretty soon. So it just made sense for that reason. But it doesn't mean I need to go into this topic incredibly deeply. So, well, it means we certainly have time to talk about any homework questions if anybody has them. Because there's a lot of unsubmitted homework floating out there.
Hey man, I just finally got caught up, okay?
Okay, yeah.
I got the last one submitted.
Yeah, which, relatively speaking, puts you ahead of the game.
I came back this last Monday, so I'll submit it this week.
Okay, yeah. Well, because there are 13 people in the class, and I think 5 of them have turned in homework 2. So you get the idea of where we're at. Because what I'm covering today, to reinforce the review, I did put a homework in there, and so today's material goes to homework 5, which is not due. Okay, due doesn't mean anything in this class, obviously, but is recommended finished after spring break. So there's plenty of time to catch up on things, but please do, because last semester I had a lot to grade at the very, very, very end, and thankfully the class is smaller this time, but I don't want it to get like that if at all possible, because also that's harder on you too, so something to think about. I like to be flexible, but really now. So that means that there could conceivably be questions on homework 2, 3, or 4. And again, I'm flexible. So does anybody have anything?
Can I ask from 3.23?
323. Wait.
Homework 2.
Yeah.
For number 4B.
Oh, let me pull it up. Okay. This one? All right. Oh, yeah, I know people have been struggling with this one.
Yeah, so for like matrix, we're doing the arbitrary matrices, right?
We're doing what?
Arbitrary.
Yes. Yes, the idea is it should work for a general matrix. Now, from a specific case, you may be able to get an idea of why it works in general, so it can still be helpful to you. But
Yeah, but how do we find inverses for those arbitrary?
Okay.
Are we doing like the, what is that called? Like linear algebra?
There you are. Okay. Thank you. Glad you're here. Okay, so for this problem, it is not expected that you would actually have a formula for the entries of the inverse. So really, okay, let me phrase this more clearly. Okay. Well, okay, since I have an announcement section, I'll fill in what I was just talking about. Gotta soften that up a little bit. Okay, so, okay. All right. So for this one, in showing that, okay, so I'm focusing on the case of lower triangular matrix L is lower triangular. What you can do is can show that the solution of this system L xj is equal to ej, where x is equal to L inverse. So in other words, this is column J of the inverse. And EJ is the jth column of identity. Has all elements x1, actually I'm going to write it this way, 1j, x2j, and so on, up to x j minus 1j equals 0. So I don't want to say all elements. I don't mean the entire vector, but so if you can show now this the right hand side has all elements 0 except for the jth one is equal to 1 because it's a jth column of identity. So what you're doing is you're carrying out forward substitution to solve this system because L is lower triangular. So if you can show it for this situation, because the first j minus 1 elements of this vector are 0, that would lead to the first j elements of this vector, xj, to also be 0. That would lead to L, the inverse being lower triangular. Okay. So put another way, that xij equals 0. Xij equals 0 for I less than j. X is lower triangular. Okay. Okay. Now, to make things a little easier, or at least less tedious in this problem, because the way the problem is stated is, okay, the inverse of a non-singular upper-lower triangular matrix is upper-lower triangular. No need to repeat the whole proof for upper triangular after doing lower triangular, because use the fact that if A is non-singular, then A inverse transpose is equal to A transpose inverse, which therefore has a common notation A minus transpose, because it doesn't matter which thing you do first, inverse or transpose. So if you've covered the lower triangular case, Then to talk about the upper triangular case, you just work with a transpose, and B's properties will give it to you quickly instead of having to do all this IJ crap. So, because really, once you've shown it for lower triangular, it's not really interesting after that.
So, I mean, I've already submitted this.
I don't care which way you do it.
But like, I mean, I did it this way, but I was thinking like we could just, I mean.
Well, yeah, you kind of reverse things. Yeah.
Like the product of the lower triangular matrix and the inverse is an identity matrix.
Yeah.
And so the identity matrix is triangular, and that's also triangular. So the inverse matrix is supposed to be triangular, right? I mean, if I use the property A.
Oh, from a product.
Yeah.
Let's see. Let me think about that.
Then we are just done in two.
Well, but it's almost like backwards reasoning of it. Okay, like you have like L times the inverse is identity. Okay, so triangular times something that you don't know yet is triangular.
Yeah.
So it's not the same statement. So you can't really backtrack from that to say, oh, then this must be triangular.
I mean, I didn't use that.
Oh, okay, well, good. Yeah, because that would have been flawed. Okay. All right. Okay. Okay.
3.3.3.
333. Okay. All right.
So do we have to store the subdiagonal, superdiagonal, and the diagonal entries in a vector, or we have to do that in 334?
Oh, let's see. In this problem, vector storage is not required. Because if it was, then I would have to describe its function differently, different parameters. Where instead of passing a matrix A, I had to put 3 inputs, like for the subdiagonal, diagonal, and superdiagonal.
So
Yeah.
you don't want us to use those.
Well, if you want to, I don't care, but I'm saying you don't have to.
Okay.
But you mentioned, okay, this one has to work with vector storage. I guess what you're saying is that you could do 2 problems at once if you want to.
Yeah, if I use vector in that one, then it's
well,
the same.
Let's see. Well, that would cover part A. Anyway.
I won't get to see the combination.
Yeah. So part B goes beyond tridiagonal for a general Bannon matrix. Wait, what?
I'm not sure I did not see. I'm just seeing it.
What?
Like I don't remember doing. I've submitted this, but I don't remember doing 3.3C.
You're not sure if that's included in your submission?
Yeah.
Oh, okay. Well, I mean, if it's missing, I'll just let you know. Okay, yeah. Yeah, I mean, as a rule, if something is just missing, I'll let you include it. So.
So I have a question on 3.4.
343.
Yeah.
Okay. Yeah.
Yeah. So because it says you should calculate the condition number. So are we doing that on MATLAB?
Yeah, this has to be done in MATLAB.
So just the condition function.
Yes. Yeah, because condition number in general is something that's not easy to just compute by hand.
So when we do that, what are we actually turning in for this?
Okay, so what I'm looking for you to turn in is this plot. So saving it as an image and including that. Also, be good to include the MATLAB code that creates it So if something's off, then I can look at that. So when I say values at n ranging over several orders of magnitude, like powers of 2 or 10, so you can work with like a matrix that's 100 by 100, 1,000 by 1,000, or 10,000 by 10,000 of this form, and computing a condition number for each. And the cond function, COND, that computes this by default, the 2 norm.
So when we're plotting this relation, I need to say we use the log function.
Yes.
So are we fixing like log function and using K2 of A and an input argument?
What you could do is you can make 2 vectors. One vector of n values, whichever sizes you chose for your matrices, and then the other would be a vector of the condition numbers. So you can plot one vector versus the other. And maybe just doing three matrices would be enough to show what the trend is. Yeah, because when I've given this problem in the past, now and then I've gotten some strange-looking submissions, like for a plot. So then I can look at the code and see, oh, this is what went wrong. So what you could do is suppose n is equal to 10 to the p. So like I said, it's a suggested problem using powers of 10. Use a loop for p to create each matrix and get its condition number. And you can store both in vectors. So for example, condition numbers. So something like this, like in the loop. So you have your A of whatever size, computes condition number, and it's stored in the ith position of this vector. Then when the loop is done, then you use that vector to make your plot. Same thing for storing sizes of a matrix. So you have these 2 vectors at the end, vector of sizes, vector of condition numbers, to log plot one against the other. Okay. Other questions about any pending assignment? Or you can always ask them later. Okay.
Like I was trying to check the function I wrote for. And that's 3.2 points. 20.
Oh, yes, that one. That seems to get a lot of questions.
What does it affect my grades? Because I've already done it.
Oh, well, I'm pretty generous with partial credit, so.
Okay, so when I wrote the function, I tested it on a random vector and used the a bar slash b.
Yeah.
I got the same result.
Okay.
But when I do use LUP,
Mhm.
MATLAB inbuilt function
Yeah.
to get every decomposition and computation matrices.
Yeah.
I did that and used that and compared to my code. My LU decomposition was kind of different.
Oh, then MATLAB's LU?
Yeah.
Um,
And I was
okay. Because MATLAB's LU is supposed to do Gaussian elimination with partial pivoting. But the output is kind of strange, depending on how you called LU. So you called LU to get outputs like
so I did LUP.
yeah.
So I gave the LU and implementation matrix.
Okay. And if it didn't quite match,
Not exactly. It was very similar, but like the row swapping was a bit different.
okay.
I didn't know that.
Yeah, like I don't know if there's a difference, like in case there was a possibility, depending on the matrix of. Did you generate like a random matrix or something, or?
I actually use one of the matrices from the textbook.
Okay, because in some cases there might be a tie as to which element to use, and ties could be broken differently. I would suggest testing it like on a random matrix. It'll generate floating point numbers, so that in that situation won't happen. And see if there's still a mismatch. So, I mean, since you're getting a correct result and you are doing pivoting, if there is something that's actually wrong, it would definitely not affect your grade very much. So, but yeah, that's it's interesting. If it continues to happen on a random matrix, but it still gives a correct result. So. I haven't looked at the homework twos yet because not many people have turned it in. I try to wait till there's like a critical mass and then I look at all of them because I don't want to ruin a weekend until I really need to. But I gotta be curious now to go look. All right. Any other? Okay. Well, at least it's not a monsoon outside right now, but.
Give it a little bit, it'll come back.
Okay.
It's supposed to be like raining like midnight or something weird.
Yeah.
Yeah, well, apparently according to the iPhone weather app, I guess the rain kind of takes a break for a little bit, and then at 8 o'clock it comes roaring back.
And it starts raining at 5:15.
Yeah, okay. So, whatever. That's Mississippi for you. Okay.
I gotta be honest though, I was not expecting it to rain more here than it did in Florida.
Okay.
I'm very upset about that.
You don't like rain?
No!
That's so fun.
You're crazy.
Okay. So, what we'll be seeing later on in the semester are solving systems of nonlinear equations. Now, last semester in 460, I covered solving a single nonlinear equation. And so there's portions of that material that I think should be reviewed, and that'll set the stage for talking about systems, because surely all that stuff's been forgotten by now. Okay, so to solve a nonlinear equation of form fx equals 0, we can rewrite in many ways form x equals g of x. A simple example, you can let g of x be equal to x plus lambda f of x, where lambda is non-zero. So then, if f of x equals 0, this term drops out, and you have x equals g of x. But there are other ways too. So this leads to algorithm, very simple algorithm fixed point iteration. So what is the algorithm? I'll just put it out here real quick in pseudocode. Okay, so first we choose an initial guess. Oh, I need to be able to do some indentation here. Okay, so we choose initial guess, x naught. Okay, and then in a loop, okay, what we do inside the loop is we set the new iterate x k plus 1 is equal to g x k. And then what we do is we use xk and xk plus 1 to check for convergence in some way. So for example, maybe we see if an absolute value difference between these is less than some small value, like 10 to the minus 10 or something like that. And if so, then we quit. So so that's all we do is we keep substituting the old iterate into G to get the new iterate. Then that gets substituted into G. We just keep substituting until we see some convergence, or it becomes clear that it's not converging, and then so then we have to give up. So some examples. Okay. So first example is solving f of x equal to x minus cosine x. So really what we're solving is equation x equals cosine x. So the g in this case is cosine x. My second example will be f of x equal to x squared minus x plus 3/16. Okay. Or solving x equal x squared plus 3/16. Now, we could figure out what the solutions are supposed to be using the quadratic formula or factoring. But just to demonstrate what could happen in this kind of iteration. And then the third example will be f of x equal x plus ln of x. So x equals minus natural log of x. And a fourth example, f of x equal to, this one's my favorite, x minus cosine x minus 2, which can be written as x equals cosine x plus 2. Okay. So what happens when I try fixed point iteration on these four, the second versions of each one? Okay. Now, so what I'll do is try this in MATLAB. Okay. So what I'll do is I'll pick an initial guess. I'll pick x equal to 1. Certainly, whatever we get should be between minus 1 and 1 because it's a value of a cosine that's between those two values. So I'll just try this and see what happens. So all I'm going to do is just set x equal to cosine of x. And I'm going to do format long here. So we get 0.54. And now if I keep going, it's jumping around. But let's see if it continues to jump around or does it show some signs of converging. It appears to be converging because the last several iterates have been like 0.73, 0.74, thereabouts. And if I keep going, the iterates are coalescing. Like we have 0.73908, but the other decimal places are still changing. But if I keep going, we will eventually see, whoops, all decimal places staying the same. It's taking a while. I've done this maybe 50 times by now, and I'm not keeping track. But notice everything is now stationary except for the very last few decimal places, and those are getting closer. And I think it's just about done. Okay, yeah, so finally we got all decimal places to agree. So that is the fixed point. So what we can say is converge, but slowly. Okay, but at least it converged. Now, for the second example, so if we use a quadratic formula, the solutions are, so x, I use x star to refer to the solution. There are two of them because it's quadratic, so 1/4 and 3/4. Okay, so what I'm going to do is try initial guesses that are at least close to these values to see, all right, if I pick something that's in the ballpark, does it converge? So for my initial guess, I'll choose like 0.2. So it's pretty close to the first solution of 1/4. So I'll do x equal x squared plus 3/16. Okay, so it didn't wander far away, and actually it is getting close to 0.25. Notice we see more and more 9s lining up as it's getting towards convergence. Okay, so at least that worked. Okay, and we hit 0.25. Okay, now let's do the same thing with the other solution. I'm going to choose 0.8. So you think, oh, okay, I'll try this iteration. It should converge to the other solution, 0.75. Let's see what happens. That's not good. It's going in the wrong direction. And further, oh, this is hopeless. It got hopeless pretty quickly. So that's odd. So what if I try something on the other side of 0.75, so 0.7? Should it converge in that case? Well, it's going the wrong way again. It's decreasing. So it's actually heading towards the first solution, 0.25. Looks like it's eventually going to get there. So what we can conclude is converges to 1/4 unless x is greater than 3/4, in which case it diverges. Okay. So we have to have some idea as to what is it about a solution, this fixed point iteration, that can we tell up front that it's going to converge or diverge. Okay. Next example. X is equal to minus. So log in MATLAB is natural log. There's also a function log 10 if you want log to base 10. So now if I look at this, if I pick x as 0.5, x plus log x is negative. If I do x equals 0.6, then it's positive. So because this function is negative at 0.5, positive 0.6, by the intermediate value theorem, solution exists in 0.5, 0.6. Derivative is 1 plus 1 over x, which is positive for all x in the domain. In other words, the function's always increasing. If you have a function that you know it has a root, so we know it has a root between 0.5 and 0.6, but the function is always increasing. What that tells us is the root's unique. Okay, so for the third example, for a solution in 0.5, 0.6. Okay. So I'll choose 0.55, a midpoint. So about how you can tell, why does this mean the root's unique? Suppose there was a second root. The function's 0 at a certain point, and if it's 0 at a second point, well, the function is increasing, it has to decrease eventually to get back to 0. If a function's always increasing, it can never come back. So that's how you can tell uniqueness. Okay, so 0.55 our initial guess. So now do x is minus log of x. All right, it's still in the interval, barely. But if I keep going, it's all over the place now. Now it's complex. It's taking a log of a negative number. So that didn't work. Iteration, initial guess, 5 diverges. So here's what I'm going to do. I have x is minus natural log of x. So what I'll do is I'm going to negate both sides. Minus x equals natural log of x. I'm going to take the exponential of both sides. And what that gives me is I have e to the minus x on one side and then x on the other side. So basically I'm taking the inverse function of both sides. So in fact, the inverse of minus natural log of x is e to the minus x. So, okay. So let's try this instead. I'll go back to 0.55. I'll do e to the minus x is e to the minus x. Much better. All staying in the interval. Is it converging? It appears to be. Rather slowly, but it is. Okay. Okay. So, what is it about certain g of x's that leads to convergence, and in other cases diverge? We don't know yet. Okay. Now, last example. I'm going to choose initial guess. Now, cosine x is between minus 1 and 1. So cosine x plus 2 is between 1 and 3. So I'm going to choose an initial guess equal to the midpoint of that, so it's 2. So all right, so x equal to 2. And what I'm going to do is I'm going to make a vector of x's using a linspace function, a bunch of x's between 1 and 3. And I'm going to plot my function, cosine x plus 2. Okay, so there it is. And then on the same plot, I'm going to plot f of x equals x. The red dashed line. So where they intersect is the solution. So g of x equals x. And it's right around 1.9. It's hard. I'm going to try to make this easier to read. Okay. Actually, if I can make it bigger still. So, all right, so we have actually more like 1.8 is where the solution is. Okay. So, here's my initial guess. All right, so first I want to find a function handle. G is cosine x plus 2. So now I want to plot x, g of x, using a red circle. So there's my initial guess, right here. So now I'm going to, I just want to make this plot more to scale. Okay, because this is y equals x, so it should be a line of 45-degree angle. So now I'll perform an iteration, x equals g of x. Okay, so now it's a bit further away, so 1.58, and I'm going to plot again. And here it is, over here. So it's like it reflected across the line. Didn't seem to make progress in terms of distance. So now I'll do it again. X equals g of x, back towards 2. And it's difficult to see. Maybe if I zoom in, you can see 2 circles here. So the third iterate is very close to the first. So if I keep going, now we're back over here. So this is kind of painful because it just keeps bouncing back and forth and still pretty far away from a solution. And see, now we have 3 on each side. So we have that back and forth effect going. Now we are getting closer to this solution, but very slow. So I want to try something different here. What if I can, since I know what each iterate is going to be, like I plug in a G and then I plug in a G again, what if I set my iterates to be the average of 2 consecutive iterates? So in other words, what if I try this? X is equal to x plus g of x over 2. So it's so this is the iterate I would normally use, and this is like the previous one. So now I take their average. Let's see what that does. So I'm going to go back to 2, and I'll say x equals x plus g of x over 2. And now I'm at 1.79. I'm going to use black circles this time. And look, it's really close to the solution. Let's do it again. And closer still. So, taking the average of 2 consecutive iterates, just the idea comes from the graph. Wouldn't have thought of it otherwise. Seems to really nail it. But we still like to have a better understanding of why that works as well as it does. So this iteration converges rapidly. Okay, so we want to have some understanding of why all of these examples behaved in the way they did. So there's some theory involved here. So about existence of a fixed point, which is the solution. All right, so that is Brouwer's fixed point theorem. That g of x has a fixed point in the interval AB if g maps the interval AB into itself. So, in other words, if I plug in any value in AB into G and I get a value that's also in AB, then a fixed point exists in AB. The proof use the intermediate value theorem. This is actually a really short proof. Okay. You're looking at the function g of x minus x. So the idea is it is negative at one endpoint and positive at the other. Therefore, it must have a 0 in between. It's the principle behind the bisection method. Okay, so that's existence. Now, uniqueness, if G has a fixed point in AB and satisfies a Lipschitz condition on AB, meaning that difference in G values is less than or equal to some constant L times the difference in X values, where L is less than 1, and that is a Lipschitz constant. So if G satisfies this condition, then G is a contraction, and the fixed point is unique. So we already know it exists, but now we know that it's unique. And fixed point iteration will converge for any initial guess in the interval. Okay. This is called the contraction mapping theorem. Okay. So now we have some idea of when fixed point iteration can actually work. The trouble is this kind of condition, Lipschitz condition, is difficult to verify directly. But here's something to think about. Another way to look at it is from the fixed point theorem, which is actually a disappointingly generic name, but I could not find another. By the mean value theorem, we have a following. If I look at g of x minus g of y over x minus y, well, that is equal to, by the mean value theorem, g prime of some unknown point in the interval containing x and y. All right, so that's what the mean value theorem says. So we can take that and run with it. So if g prime x is less than or equal to L, which is less than 1, on AB, then we can say that G is a contraction. And L is a Lipschitz constant. So that actually works. Okay. And this could be easier to check. You can go ahead and take the derivative and get an idea of how big it is on the interval in question. And if you can bound it by value less than 1, then you know that then you know it converges. Okay, so now what I want to do is revisit these examples in light of this information. Okay. So, for x equals cosine x, g of x is cosine. So g prime is equal to minus sine. So it is a contraction on an interval, let's just say 0 to 1. So if we stop short of pi over 2, then we can say that the derivative is less than 1 in absolute value, or it's bounded away from 1 in absolute value. So that works. Notice it's not enough to say that g prime is less than 1. It has to be less than or equal to some constant that is less than 1. Sounds like I'm saying the same thing. I'm not. The point is, g prime is not allowed to get arbitrarily close to 1. It has to be bounded away from it. So there has to be some meaningful gap between L and 1. But we can see here why it converged. But if we look at the fixed point that we got, I have to scroll up here quite a bit. Hopefully I still can. Okay, so notice the final fixed point was like 0.739. So what's the derivative? Wait. All right, so this is what it is. Now, it's less than 1 at least, but it's not very small. It's greater than 1/2. The bisection method will be faster. So g prime at the fixed point is not very small, so convergence is slow. All right, so if we look at g prime at the fixed point, that gives us an idea of how rapid convergence is going to be. So that's the first example. The second example, x is equal to x squared plus 3/16. G prime of x is equal to 2x. So we have g prime at 1/4 is equal to 1/2. G prime at the other fixed point, 3/4, is equal to 3/2. So because g prime at 3/4 is greater than 1, that fixed point is unstable. So you may have a fixed point, but if a derivative is greater than 1 in magnitude at that fixed point iteration will not converge to it. Whereas the iterates are drawn to this fixed point, 1/4, where the derivative is less than 1. Okay, and then for the example, x is equal to minus natural log of x, or minus ln of x. So if I look at so minus log of 0.5, and oh wait, that's not what I want. G prime of x is equal to minus 1 over x. So if I look at minus 1 over 0.5, it's minus 2. So g prime is greater than 1 on 0.5 and 0.6. So that is why fixed point iteration diverged in that case. But for the next choice of g, e to the minus x, right, so g is equal to e to the minus x. We have g prime equal minus e to the minus x. And that is going to be less than 1 in magnitude. And here's how you can tell. This differentiation rule for inverse functions of a derivative of f inverse of x is equal to 1 over f prime of f inverse of x. Okay, so in the case of f being g, if g prime is too large, use the inverse function. You're taking 1 over derivative, so if g prime is too large, the inverse of g prime will be sufficiently small. That's x equals g of x is equivalent to x equals g inverse of x. Why? Take this equation, apply g inverse to both sides. You have g inverse of x on the left, plain old x on the right, because g and g inverse cancel each other out. So if you can't solve this equation because the derivative of g is too large, just go to this one if you can, if you can work out g inverse. So if this one fails, you know this one will succeed because you're taking a reciprocal. Okay. And finally, the fourth example, x is equal to cosine x plus 2. G prime of x in this case is minus sine x. And the fixed point was around 1.8. So let's see how big that is. So minus sine 1.8. Oh, it's almost 1. So it's nearly 1, thus convergence is slow. For the new g of x, the new iterate, I'll call it h of x, is x plus g of x over 2. We have h prime of x, which is equal to 1 minus sine of x over 2. Well, if sine at the fixed point is nearly 1, then the derivative of h will be nearly 0. So that's why convergence is much faster in that case. So if you can make the derivative small in a neighborhood of a solution, then you know a fixed point iteration will converge rapidly. Okay. Now, what we can also say is Taylor expansion of G to analyze the error. So if I could do the following, x k plus 1 minus the solution x star. Well, xk plus 1 is g of xk. And x star is g of x star, because x star is a solution. But what I can do is I can Taylor expand g around x star. And that Taylor expansion would give me g prime of x star xk minus x star plus 1/2 g double prime of x star, whoops, where'd it go? Okay, times xk minus x star squared, and so on. So here's how the new error after k plus 1 steps relates to the old error after k steps. Notice, here's the error after k steps. This is the old error. Notice it's multiplied by g prime. That's why we want g prime to be less than 1 in magnitude. So the error will actually get smaller. The smaller it is, the more rapid the convergence will be. But now this also shows a special case. What if g prime at the fixed point is 0? So normally, convergence is linear. In other words, the new error is proportional to the previous error. And the proportionality constant is this g prime. With asymptotic error constant, g prime, absolute value, at the fixed point. So that indicates how rapid convergence will be. If g prime at the fixed point is 0, this term goes away, and this is the leading error term. And notice the new error is proportional to the old error squared. We like that because that means if the error is already small and you square it, it's a lot smaller still. So then we say convergence is quadratic with asymptotic. The asymptotic error constant is just a constant proportionality. So it's just a g double prime at x star over 2. If a second derivative is also 0, then it'd be cubic and so forth. Okay. All right. So that's the idea behind fixed point iteration, that we can just make an initial guess and keep substituting into our function g to solve x equals g of x. And we like the derivative of g to be small near the solution. If so, then first of all, the iteration can be short of converging, and hopefully it's small enough to ensure a rapid convergence. Now, later on, we'll see this method applied to systems of nonlinear equations. So the idea is g is a vector-valued function of several variables. So we need to adapt the notion of a small derivative to the multivariable case. That's what leads to a use of a Jacobian matrix that you may remember from multivariable calculus. But I'll certainly review all of that when the time comes. Okay. There is one part I did not get to, but all right. But I only have 5 minutes left. Okay. You know what? I'm going to hold off on that till next time. So, okay. So that's what this realization part is. I'll just wait. Okay. So there you have it. So try to keep the homework coming. And I'll see you on Monday.